Okay, welcome. We're gonna get going. So, what midterm do you guys have today? Oh, are you the people who don't know you have a midterm? Did I spill the beans? So, what is it? 231? Okay, good luck. So here's a break from studying for electronics. Okay, so we're talking about pathfinding, and we started looking at depth first search. Let me turn this down a little bit. Okay, so this was our first pathfinding algorithm. It's a recursive algorithm. It's very similar to the algorithm you use to find things in a binary search tree in 244. And we went through the code at the end of last lecture, so I'm just going to show it again. But then let's walk through on this little graph what happens. Okay, so we start by calling our find path algorithm at our source, right? So the node that represents the intersection we're at. We check, am I at the destination? I'm not at the destination, so I don't return. Instead, what I do is I look at some data for the node I'm at right now. So I'm at this current node. And the data I want is what can I reach? So what are the outgoing edges from this node? So street segments that I can travel down. And you wrote functions in milestone 1 that should be useful for this. So I'm going to look from this node, where can I go? And the first edge that I look at is this one. It goes to node 2. So I say, okay, what I'm going to do is recurse. I'm going to call this find path algorithm again. And now my current node is node 2. And I'm still looking for my destination. So that's my recursion. Call it on this node that I can reach. Okay, so I go through the same procedure, come back up here, I check, all right, is that my destination? It's not. So I go down into this code again, but now I'm at my current node is node 2, I'm right here. So I only have one outgoing edge, I look at it, it goes to node 3. So I call the routine again with node 3, it's not my destination. And node 3 also does not have any outgoing edges. Okay, so I get to this loop, there's nothing to do. So I just return false, which what that means is I basically return from the recursion, and I'm back at node 2, because node 2 was only partly done. That was on my stack, right? Node 2 I called find path. But that was for the first edge from node 2. Node 2 actually has 2 edges. So now I'll go look at the other one, which goes to node 3. So I'm going to call find path on it. That's my recursion. And node 3 is not my destination, but when I get to this part of the code, I look at its outgoing edges. One of them leads, well, the only outgoing edge needs to node 4. I call find path with node 4. That is my destination. Okay, because I've found my destination, I go in here. Actually, I don't go in here. I found my destination, I return true. Okay, so at this point in the recursion, I return true. And that takes me back to here, right? Node 3 was in the middle of this recursion. And basically, because I returned true, it says, well, I should also return true. So I return all the way back, basically, through the whole routine, all these recursive copies on the stack, and I return true, and I found a path. Okay, so does everybody understand how this works? It's basically very, very similar to what you wrote in 244 for a binary search tree. You're recursing through. Okay, let's see if this always works. So it worked fine on that graph. I found a path. Let's say I take this slightly more complicated graph, where I've got some intersections that are two-way. Right? So for this intersection, I can go to this one, and vice versa. So I've got some two-way streets. Same code here, but if I walk through this, I start at the source, it's not my destination, so I look at its outgoing edges, call my recursive routine, so I'll go there. That's not my destination, look at its edges, call my recursive routine, I'll go there. Keep going, I get to this point. Okay, this is also not my destination, and let's say that in this loop that goes over all the outgoing edges, the first edge I look at is this one. Okay, that goes back to a node I was already at. And at that node, I go through this loop, and let's say the first node edge is this one. So I go back to this node on the right, and that'll just continue forever. Okay, so I actually have an infinite loop. I'm just going around in circles, basically going the same city block, up and down, up and down, up and down, hoping I'll get to my destination, but that's not going to happen. Okay, so we've got an infinite loop here because we're recursing back and forth. This never happens in a binary search tree. So I told you this code's very similar to what you have in a binary search tree. The structure of a binary search tree ensures this will never happen. Binary search trees don't have loops like this. What I've drawn here in a graph is called a cycle. It means I can go around in a circle. By following some number of edges, I can get back to where I started. That cannot happen in a binary search tree. But it can happen in a general graph, like a street graph. Okay, so our code isn't working. How do I fix this? So does anybody have any ideas of how to fix this? It's not that hard. A hint is that I've added a couple of blank spaces in the code. That is actually sufficient to fix this. So what do you think we should do to fix? Any ideas? So generally, you're going to need some more data. So if you're thinking, well, can I fix this just with code? No, you got to say, okay, I'm going to have to store something. All right, that's the way you're going to fix this. If you were doing this as a human, right, the algorithm that we're using is basically, you go to a node, you check, if I'm trying to get to D or E06, I check, am I at Z06? I'm not, so I'll pick someplace else I can walk there, and so on, and keep doing this. And my current problem is I tend to keep going in loops. I get here, and I say, oh, maybe I'll go back here. And I get here, and I say, oh, maybe I'll go back here. So now I wouldn't actually do that, because I remember that I was already here. So we need to do something similar in the program. We have to remember that we were already at this node, so we don't recurse. We don't keep going to it over and over again. Does that make sense? Okay, so the way we do this is we have to add memory. We have to add some storage. So I made this vector that I called nodes. So there's one entry for every single node ID or intersection ID. And the reason I made this vector of some type node is so I can just keep adding data to it. So I've now just basically added some data to this structure. I've added a new variable called visited. So every single node I've got a visited flag for. Before my routine starts, this path search routine starts, I have to make sure all these visited flags are set to false. Okay, I haven't looked anywhere. But now what I do is when I reach a node, I still check, are you my destination? But if it's not my destination, I record, I have been here. Okay? And then when I get into this loop, which is look at everywhere that I can get to in one step, what can I reach, and call my recursive routine on all those nodes. Before I do the recursion, before I go and visit a node again, I look at it again, I call my recursive routine on it, I check, have I already been there? If I've already been there, I don't want to look at it again. And this will stop my infinite loop. It will stop me from looking at nodes that I've already done. Does that make sense? Everybody see how this works? So this notion of a visited flag is a common thing you have to use in graphs. And if you write recursive routines in a graph and you don't have a visited flag, you will go in circles. So we've stopped that by recording, have I been here before? Okay, so let's visualize how this works. So we started our source, call our find path routine. That's not our dest. We're going to mark it as visited. So I've colored it red to say I've marked it as visited. And then I'm going to go look at where can I get to from here. So I look at this first edge, and I see I can get to this node on the right. It's not my destination. I mark it as visited. And now I look at its edges to see where can I get to. Let's say I go up first. Not my destination, mark it as visited. I look at its edges. Let's say I go right first. Not my destination, mark it as visited. Now, I'm going to look at this edge, okay, which goes backwards. This was my infinite loop problem. But when we look at that edge, this if statement here says, the node on the other side of that edge I've already been to, don't do anything. Just skip it. Okay, so that edge now I've looked at, it's done. And I'll look at the other edge coming out of here, right, because this loop goes over all edges. And I'll find I actually found my destination. Okay, so now I've found my path. Does it make sense? So code's pretty succinct. Now what output can I give? In milestone 3, you're supposed to return the path. And we said a good way to encode it, and the way that we're asking you to encode it, is a vector of street segments that is in order and tells you how to get from the source to the destination. What do I know at the end? So I actually know very little, right? When I return, right now my routine just returns true, okay? If I found a path, and it returns false if I didn't. So this is probably the worst directions ever. Okay, so you ask, how do I get from Spadina in college to Steeles and Jane? And the answer will be, yes, you can get there. Okay, it's not going to tell you how, it'll just say it's possible. But if I asked, how do I get to the Toronto Islands from here? It'll say, no, it's not possible, okay, because there's no road that goes there. But this is not very good travel directions. We could fix this. So we could store some more information and fix it, but I'm not going to fix it for depth first search. We'll fix it later when we have a better path search algorithm. Because I'm going to show you this algorithm still, for our purposes, isn't that good. Okay, so I showed this to you because it's actually an important graph algorithm, and it's one that a lot of students think of because recursion is something you've used quite a bit in 244. But it's not a great algorithm for us to use. Let's see, it's like binary search tree find operation you wrote in 244, but we need this visited flag. That's the big difference. Our graphs are big. You know, pretty much all our maps are more than 100,000 nodes. Toronto's 200,000, Tokyo's 1 million. So one of the things we want to see is how fast is this? And we're going to call the number of intersections, or the number of nodes in our graph, n. Okay, so this is the code for depth first search. I don't know, in 244, did you analyze? You probably analyzed the complexity of recursive algorithms like this. Is that right? Does anybody remember that, doing that? Okay, so you vaguely remember it. Does anyone want to take a shot at what is the complexity of this algorithm on a street graph, the kind of graphs we're using? Because it turns out the complexity of this algorithm will vary a little bit depending on the properties of the graph. But we're going to do it in a street graph. And if you don't, I'll walk through it. But if you think you know the answer or you can walk through it, buzz in and I'll call on you. And if not, I'm going to start going through it. Okay, so it seems like nobody's quite bold enough. So an algorithm like this, it actually looks harder to analyze. You kind of don't see nice loops where you can say, oh, there's one loop from 0 to n, and there's another loop from 0 to n, so it's n squared. I don't really see that here. It's a recursive algorithm, looks harder. So the way to analyze this is, because I mark every node as visited once I see it once, and I will never look at it again, right? So I mark a node as visited when I get there, when I make my recursive call, and then I'll never look at it again because I actually check, have I already visited there? So that actually guarantees that I will never call find path more than once per node in the graph. Can't happen because of my visited flag. So now that simplifies my analysis a lot. Now I just need to know, well, then for one pass through this routine, what's its complexity? Because if I multiply that by n, I've got the overall complexity. Okay, so one pass through this routine basically just has this loop. Okay, there's like a few constant time operations, and then there's one loop here. Now this loop goes through all the outgoing edges of a node, and we know that there aren't very many edges per node, because in a street graph, we just can't make an intersection connect to a huge number of streets. Normally it connects to maybe 4 street segments. Maybe you could make a city where it connects to even 6 or even 8. There's no possible way you can make it connect to 100,000, right? Like this intersection has 100,000 streets converging and every intersection is like that. It's not possible. So this loop only executes a small number of times. Number of edges is maybe 4, maybe it's 6, doesn't really matter, it's a constant. So because of that, this whole routine is order n, okay? Because we can tell that it only gets called once per node at most, and that it does constant time work every time we call it within the routine, right? Not including the fact that it might call itself, because we already took care of that by saying it can't be called more than n times. Does this make sense? Okay, I hope you're with me. Okay, so our worst case complexity is order n, which is actually pretty fast. So depth first search is a pretty fast pathfinding algorithm. Let me show you what it looks like. So let's see here. Okay, so this is, I've written depth first search in our reference solution, so we can run it on a street graph, one of the city maps, or any city map. And I'm not going to show you all of this, but basically I've also used the graphics from my milestone 2 so I can draw all the street segments that I'm looking at. As I explore a street segment, so a street segment is an edge, whenever I look at that edge and I go to the other side of it, I draw it, okay? I draw it kind of thick. That will actually draw fast enough that it's hard to see the algorithm. So I'm calling this delay routine, which I'll show that to you in a future lecture. But basically I'm saying delay by a millisecond, which isn't that long, but it's going to slow down my graphics quite a bit so you can see them. All right, so let me shrink this down. And I think I've already compiled this. I have. Okay, so basically over here, I can actually go through different path finding algorithms. And the only one I've shown you so far is depth first search. So that's the one I'm going to show you. So if I click on an intersection, it's actually going to go find a path to it. Okay, so it started here, and it's trying to find a path to the intersection I clicked on. And so you can see how it's exploring the graph. Does this look like a good Uber driver? Like if you had an Uber driver who was doing this, would you be impressed? Is this like, you know, when it brings up the like 15% tip, or you're going to go all the way to 20 or maybe even 25% tip? What do you think? This is like a negative 1,000% tip. Like you want this driver to like, okay, at some point, just give me the keys to the car. Like I'd take your car, right? So you can see that this algorithm kind of lacks intelligence. It's just wandering around the graph at random, recursing. It has no idea of where you're trying to go. It does not go in circles, so that's one good thing, because of our visited flag, it doesn't just keep going around the block forever. It will eventually find the destination, but it's kind of wandering a lot, right? It has no intelligence whatsoever. So I'm going to speed this up again, because this is going to take too long. So let me make this a bit smaller and kill it. Okay, speed this up. I'm just going to take that delay out. Let's see. So I'm just reducing that delay, and I'm going to run the mapper again. And you'll see that actually the graphics now are much faster. So a 1 millisecond delay actually makes a big difference. Okay, so now it's going to go much faster. Let's just click over here. Okay, so you saw the dark blue. That was it exploring the graph. The red is the path it took. So it did find a way to go between two places. So it went from basically somewhere on Highway 401 to Huntington Avenue and Brussels Road. And the journey is going to take you 3,800 minutes, okay, because it took you on a tour of Toronto. If I click somewhere else, it'll find a path to there. And that, this particular journey is going to take you 6,000 minutes. So it's not finding very good paths, okay? And when I slowed it down, you could probably see why. It has no intelligence to its search. It's just finding any path. Okay, so let's go back to the slides here. Okay, so the path that we're getting is not very good. We find a path. Depth first search is guaranteed to find path if it exists. That's why it's a useful algorithm in general. But it's not the shortest path. So for our purposes, this isn't a great algorithm. Okay? You're going to get pretty low marks if you start showing these kind of paths, because they would really annoy any user of your program. Okay, so how do we fix it? Okay, so let's just visualize depth first search again. Depth first search basically goes in random directions. It's just wandering around saying, is this the destination? If it's not the destination, it recurses. It just decides, let's go someplace we haven't seen and just keep going. And it will wander all over the place. If a path exists, it will eventually find it. Okay? So depth first search could find that path. Now, if I gave you a map, like a paper map, and I asked you to, I don't know what I just did, and I asked you to find say, a path between these two intersections, right? Maybe that's Spadina and College, and maybe that's, I don't know, Bloor and Dufferin. You probably wouldn't just start looking randomly around the map, right? Like where you just took your finger and started wandering around trying to find a path. What's a more orderly way by which you could look at a map or physically go search for a path? So what do you think? A lot of algorithms, you can gain intuition by thinking, how would I solve this? As we get into more complicated algorithms later in the course, that's a very useful way to think about algorithms. You think, what would I do? What would be smarter than this? And then try to code that in a program. So most people don't search a map this way. So what could you do that's a little more orderly? So what do you think? Yeah, so let's go to, let me look at your D09, I think. So what would you do?
For example, for these 2 points, I will only go either to the north or to the west.
So you're saying go towards the destination? Is that what you're saying? Yeah, so, and that's a good idea. And we're actually, as we get into more advanced algorithms, they're going to try to do that. So try to go towards the destination. To start with, I'm going to do something that's not quite as smart as that. But what I'm going to do is, it's smarter than this. I'm going to go in circles. Okay, so I could basically say, well, let's just check the intersections right around where I am, see if any of those are my destination. If none of them are, let's look at the intersections that they could reach and kind of expand outwards in like circles. Like I'm taking my finger and I'm tracing around in circles looking, can I find this destination? And if I find it, okay, I found a path. And that path will be pretty short because I was expanding outwards in kind of these circles. Does that make sense? So I start looking near where I am and then gradually expand the search outwards. You're right that if you can make this even more efficient if you know the direction you're heading by saying, well, let's focus more in that direction, and we're going to do that a little later when we enhance this algorithm further. Okay, the algorithm I just showed you visually is called breadth-first search. So there are kind of 2 classic ways to find paths in a graph. One is depth-first search that I just showed you. The other one is breadth-first search. So what breadth-first search does is it essentially proceeds in levels, or I was showing them as circles. So we start at the starting point, the starting intersection, and that's like 0 hops away. That's where I am right now. Then we look at every intersection we can reach from there by just going through one street segment or one edge. Okay, so I go in a little circle and look around, see is it right near me. If I don't find it there, then I look at all the things those intersections can reach. So I kind of go two hops away. Can I get there by following 2 street segments? If I don't find it there, I go 3, and so on. So it's essentially expanding outwards in those circles or those waves. Okay, so I'm going to write the code for this in kind of pseudocode. It's C++-like, but not full C++ code. So we're going to call this breadth-first path, or BFS path. And again, we're going to pass in a source ID and a destination ID. So the IDs of 2 nodes, try to find a path between them. Okay, so we've got to write this routine. And this routine's not going to be recursive. This is what breadth-first search looks like. So, okay, I'm just passing in those 2 IDs. Where am I? Where am I starting from? Where am I going to? I need some additional storage. With depth-first search, my storage is essentially the stack of the processor that's keeping track of all my recursions. In breadth-first search, I'm not using recursion. I need what I'm going to call a wavefront. It's a pretty common term for it, but it's not the only term. Of basically, what should I do next? Okay, so the wavefront are nodes or intersections that I can reach by just following one street segment, but I haven't looked at yet. So it's like my to-do list. This is what I should do next. Okay, I'm going to store this in a linked list, and what I want to store is an intersection index, okay, because that's like my node ID. So I want to have a list of intersections that are the things I should look at next. That's my wavefront. And the way I start the search is I just push into my list, my wavefront, the source ID. Okay, that's where I am. Put that into this wavefront of that's the first thing I should look at. And then this is the core of the algorithm. It basically, as long as there's still, the wavefront's not empty, so there's some intersection in it that I could look at, I take whatever intersection is at the front of the wavefront, and in C++, we basically have to, we do this in 2 steps. So I'm showing you kind of pseudocode that's C++-like. We get the item, which is just the ID of the intersection that's at the front of this list, and then we want to get rid of it. We want to remove it from the list, so we do that with this pop front call. So these 2 calls together get me the intersection at the front of the list and then remove it from the list. I check, have I already been here? So I still have a visited flag, and I should have set this to false for every single node. If I've already looked at this intersection, I want to look at it again, so I just skip. But if I haven't been here, I mark it as I've reached this intersection. I check, is it my destination? If it's my destination, I found a path, I should return. And if it's not my destination, I basically do something similar to depth first search. I'm going to look through every edge that comes out of my current node, where I am right now. And I'm going to look at the node on the other side of it, so these 2 nodes, for example, and I'm going to put them in the wavefront, okay? So, and if I ever wind up in a situation where the wavefront is empty, it means I have no more ideas of how to explore. There's no more stuff in my to-do list. I still haven't found the destination, so I should return false. I should say it's just not possible. I can't do it. And in some cities, you'll find there are parts of the city that are actually disconnected. They're cut apart by a lake or something so that this actually can't happen. So let's visualize what this does. Okay, so the first line here is basically I start off and I take this source and I put it into my wavefront. Okay, so that's what I did here. Then I'm going to go into this while loop. I take the source in node 0 out of my wavefront. It's not visited yet. I'm going to basically look through all of its edges, outgoing edges. I'm going to put what it can reach into the wavefront. So at this point, my wavefront is going to be nodes 1 and 2. Okay? Then I just keep going through this loop. So I go back to the top of the loop. I take the first thing out of my wavefront. Okay, so I had 1 and 2 in my wavefront. I'm going to take out node 1 from my wavefront. I'm going to check, is it my destination? It's not. So I'm going to put what it can reach, which is node 3, into my wavefront. Okay, then I go back through this big while loop, and I say, what's the next thing to look at? Well, it was node 2, so I'll take it out of the wavefront. It's not my destination. I look at what it can reach. It can reach these 2 nodes, so I put both those in the wavefront. And I go through the while loop again. I take out node 3. It's not my destination. Look at what it can reach. It can reach node 5, put that in the wavefront. Pull out node 4, can't reach anything. Pull out node 5, well, pull out node 3 again, because node 3 was in the wavefront a couple times. And now finally I reach node 5. That's at the front of my wavefront. I pull it out. It is actually the target or the destination, so I return true. I'm done. Okay? So hopefully that makes sense. You kind of have to implement this code, which you'll do in milestone 3. You'll implement versions of this to fully grasp it, I think. But anyone have any questions on this? So you basically understand the idea of how this works. Okay, so I'm going to take that as you got it, at least at some level. Okay, when I get here to the destination, what do I know? Do I know how I got here? I know I found a path, okay, and I can return true, saying a path exists. But I said that's pretty bad travel directions if you just say a path exists. Do I actually know, when I reach this destination, node 5, do I know how I got here? Can I print out instructions to the user? So what do you think? This is like a 50-50. So it's either we have enough information to do this or we don't. So who thinks we have enough information to print out to the user the path? Okay, nobody. Who thinks we don't have enough information? Also nobody. There is no third option, right? This is Boolean logic. So you got to take a shot. Okay, we don't have enough information. Okay, we actually know we got here. We didn't store anything as we were coming along this search. We don't actually know how we got here. Okay, so we can't print a message. So we want to do better than that, right? We want to give good travel directions. So we need to augment our algorithm so that it doesn't just find is there a path, but remembers how it got there. So there are several ways to do this, but an efficient way to do this is we don't need to store the whole path at every step. What we need to know is, if I'm at this node right now, say the destination, how did I get here? Okay, so if I knew that I got to the destination using this edge, whoops, and that lets me get back to this node. And if I knew that I got to that node using this edge, that would let me get to this node. And if I knew I got to that node using this edge, that would get me back to the source, and that's the whole path. So the basic idea of how you keep track of how to get here is you don't have to store the whole path all over the place. What you store is for every node, how did I get here? And you can store that just as one edge. What was the street segment or edge ID that was used to get to this node in my current path search? Does that make sense? And then we can write some code to do what's called backtracking and figure out what's the whole path. Okay, so it's like you're leaving breadcrumbs as you go along, right? Like at every intersection that you reach, you leave a little post-it note, what street segment did I take to get here? Okay, and then if you have to backtrack, you can read all your post-it notes and reconstruct your whole route. Okay, so let's look at what that code looks like. So first we need a little more information. So my wavefront in the previous code was very simple. It just stored one thing, the ID of an ID of an intersection. This is an intersection I should look at next, right? I have reached it, but I haven't really looked at it in detail. I now need to store a bit more. So I'm going to make a data structure. I'm going to call it wave element. And the first thing I need is I still need to know what is the ID of this intersection that I'm going to put in the wavefront. So I know, okay, I should go there and look at is it my destination? What can it reach? I'm also going to store, though, the ID of the edge that I used to get there. And that's so that I can find my way back later. To make the code that I'm going to show you a bit shorter, I'm also going to make a little constructor. So I have a wave element constructor. I just pass two numbers. One is the node ID, one is the edge ID, and it just makes a wave element with those two pieces of data. So that's just a convenience to make my code shorter. I'm going to need one more thing. To make this backtrace code kind of cleaner, I'd like to know when there was no edge used to reach this point. In other words, this is the start of my path. This is my source. It's convenient for me to define a special value that I know no edge would ever have that indicates, well, there is no previous edge. This is like the beginning of my path. So I'm going to define that. I shouldn't use numbers like -1 in my code, so I'm going to define a variable called noEdge that is equal to -1. And I know that in my street graph, we never give you street segment IDs that are negative. So -1 is okay to use as what's called a sentinel value, special value that means this doesn't really exist. Okay? But if you're going to do that, you should give it a name. So this is one way to give it a name, define noEdge to be that, and you should comment, what is this? Okay, so that's one of the things I need. My wavefront I need to be able to put a little more data in my wavefront. I also need to have a little bit more data in this node vector. Okay, so we defined this structure called node, and remember I created a whole vector of nodes that is storing information about every single intersection or node in the graph. And I already had this visited flag, right? We're using that to make sure we don't go around in loops. And I might choose to actually store the outgoing edges in this, or maybe I'll just compute them on the fly using my milestone 1 APIs. But I definitely want to have another piece of data, which is the edge ID, or the street segment index, of the edge that I used to get to this node, okay, in the current path search. And I need that for every single node. So this is something that sometimes confuses students. I basically need two different data structures for a breadth-first search. I need this wavefront, and that is my to-do list, right? What are the intersections that I've almost reached, but I haven't actually fully processed them? That's the wavefront. And then I need this other structure that I'm calling node, which is basically storing information about every node in the graph. Have I found a way to you already? If so, what edge did I use to get to you? Does that make sense? And the visited says, have I actually gotten to you yet? So we need these two different data structures. One is kind of like, what do I do next? And the node one is storing, here's all the things I've figured out so far for every single node in the graph. Okay, so first we have to update our searching code. So this is the breadth-first search code that I showed you before, but I've added a few changes in blue. So all the black text is stuff that you saw before. Basically, my wavefront, I've changed it from just storing a node ID for every element to storing this wave element, which has a bit more data. And when I put things into my wavefront, I start off with the source as the starting intersection I should look at, and I use the special value no edge to say there is no previous edge, right? This is where I start. I didn't get here anyway, by any means. In my main loop, right, this is my loop that keeps going through my wavefront, taking the next set of things to look at out of it, putting the intersections that can be reached from them back in it. The code looks pretty similar, but basically I'm now keeping track. When I pull a wave element, basically an intersection out of this wavefront, I still mark it as visited. Okay, well, I still check, is this, I still mark it as visited. Well, I check if it's visited first, then I mark it as visited, and now I do this additional thing in blue, which is I'm going to store for this particular node that I just pulled out of the wavefront, what is the reaching edge? So what's the ID of the street segment that I use to get to you? And I can get that right out of my wavefront because I actually stored that in my wavefront. Okay, but this is going to let me remember it longer. And that's basically it, right? Down here, I'm putting, for the intersection I'm looking at right now, this current intersection, I'm basically looking at all of its neighbors, all the intersections I can reach with one street segment or edge, and I push all of them into the wavefront. And when I do that, I'm just putting in a bit more data. Not only the ID of the intersection, but also what edge did I use to get there, or what street segment. So I didn't have to change this much. Basically a little bit of bookkeeping. Keep track not only of the nodes, but also the edges that were used to reach each one of them. Does that make sense to people? I'm going to take that as a yes. Okay, so let's watch how this works. So at the very top of this routine, I start off by saying, let's put our source into the wavefront. Okay, so our source is intersection 0 in this case, and we're going to use the special value no edge, right? I didn't reach this from any other node. Okay, so that's what I start with. After I look at node 0, it's not my destination, so I'm going to come down here. I'm going to look at all of the things that it can reach, and it can reach both node 1 and node 2. And it reaches node 1 with edge A and node 2 with edge B. So I put that in my wavefront. I basically say, okay, node 1 through edge A and node 2 through edge B. I want both those in my wavefront. And then I go back through my big while loop. I say, take the next thing out of my wavefront, my to-do list. So that's going to be node 1. So I go there. I store in the node data structure that node 1 it's been visited, and it was reached through edge A. Okay, so I've updated that there. Still not my destination, so I'm going to basically look at what it can reach. It can reach node 3, so I'm going to put that in my wavefront. Okay, and I also record that I reached that through edge E. Now I pull the next thing out of my wavefront. That's here, the very front. So that'll be node 2, and I reached it through edge B. I'm going to store that. Okay, and so on. So I keep iterating through. I didn't bother showing the wavefront the whole way, but it basically follows the same, it searches through all these nodes as it did before, but now it's going to store all of these reaching edge IDs. Okay, so I finally hit my destination, but once I hit my destination, I can return true to say I found a path, but I also left behind some information. Every node that I went through in my path search, it knows what edge was used to reach it in that path search. Remember, you could have many edges that can reach a node, but we're storing which one did we use. Okay, so now after I've called my breadth first search path search, if it returns true, saying I found a path, I'm going to call another routine. I'm calling it breadth first search traceback. And I pass it the ID of the destination node, because the traceback starts at the destination and it traces back, seeing how did I get here. We want you to return in milestone 3 this path as a vector of street segment IDs, okay? So edge IDs. Okay, so what does it look like? Well, there are a bunch of ways you can code this. I'm going to code it with a linked list. I'm going to build up a linked list because that turns out to be convenient because I can add things to the front of a linked list. And then our unit tests don't want you to return the answer as a linked list. So at the very end of my routine, I'm just going to turn my linked list into a vector. And that's not hard to do, okay? So I'm just assuming there's a function called make vec from linked list. So now the hard part is for me to actually build up this list. So let's see how I do that. This line is going to make me an empty linked list, right? Default constructor, so I've got a path, but it's got nothing in it. I'm going to define a variable current node ID. That's like the intersection that I'm at right now. I'm going to start at the destination. And every node now that was searched in my last path search, it has this reaching edge set. So I can say, well, look at my node's data structure. Look in the value for this current node ID. I want to know what is the ID of the edge that was used to reach it, that reaching edge. And we're going to call that prev edge. Okay, so that would be F in this case. That was the only edge that we used to reach this destination. I mean, it's the only one that exists, that's the one we used. Okay? And as long as that previous edge is not my special no edge value of -1, it means I know I haven't gotten all the way back to the source. So what I'm going to do is I'm going to say take that edge ID, put it into my path. I'm going to push it at the front of the path. Okay, so now my path is not empty. It has this edge F in it. I want to go look at what node is on the other end of this edge. And I can do that using some of the APIs that you used in milestone 1. So find the intersection on the other side. Turns out in this case that intersection is this one, okay? So get that node and make that your current node. So I want to move back one step, say that's now where I am. And now I can look at, well, what was the edge used to reach it? So I just look at the, again, in my node's data structure, I look up for that node ID, what was the edge ID used to reach it, and then I'm just going to keep looping through this. Okay, so in this case, my edge ID would have been E, and I'll put that into my path. And I'm using push front, so it's going to go to the front of my path. Okay, that's going to take me back to this node, A, or this node, and I'm going to look at its reaching edge, which was A. It's a valid value, it's not this no edge, so I'm going to put that into my path, and I'm going to keep going. Finally, I get back to the source, and the source I marked its reaching edge as no edge, this special value, so that'll end this loop, okay, and I'll return the path. Does that make sense? Some of this graph code you have to kind of look at carefully, because it's not a huge amount of code, but you have to get it exactly right. Does anybody have any questions on it, or is it pretty intuitive, like how did this work? So I just start at the end. Every node remembers what was the edge that was used to reach it. I just have to trace back through those and reconstruct the path. I get that as a linked list in this case because that was convenient, so I could push edges at the front. Pushing edges at the front makes the path come out in the right order, right? Because I'm starting at the destination, I kind of want to put the edges at the front, so when I get the final path, the thing at the front of the path is actually the first edge that I used, okay? So I'm kind of using push front to make sure I get the order right. And then I'm turning it into a vector because that's what the milestone 3 unit tests expect. They don't want a linked list, they want a vector. Everybody with me? Okay. And I think I'm going to keep going for a couple more minutes. So let me bring up, today I'm slightly ahead of the game, so we'll go into like a little more on breadth first search. Okay, so all of that was good, but breadth first search still doesn't guarantee it gets the shortest path. It's better than depth first search. This doesn't wander all over the map, but I'm going to show you a little more complicated graph, and we're going to see that it doesn't always get the shortest path. Okay, so let's look at this one. We always start by putting our source in the wavefront. We're going to look at and we're going to mark that as visited, so I turned it red. And then we go look at what it can reach, so it can reach nodes 1 and 2. We put those in the wavefront. We'll take node 1 out, and we've recorded also that we reached it through edge A, okay? We mark it as visited. We look at what it can reach. It can reach node 3, so we're going to put node 3 in the wavefront. And we'll remember that we got to node 3 through edge D as well. Okay, so our wavefront, if I go back here, the next thing in my wavefront is, so let me go back, okay. So the next thing in my wavefront after I've done that is actually node 2, okay? So I'm going to go back, take node 2 out of my wavefront, mark it as visited, and I go look at what it can reach. It can reach this node, but that node's already been marked as visited, so it won't do anything, okay? And when I go and look down here, I pull node 3 out of my wavefront. Still not my destination. I look at what it can reach, node 4, so I put that in my wavefront. I'm going to fix that actually. So I put node 1 in my wavefront, but when I pull it out, I notice that it's visited, so I don't do anything. Okay, so I don't update the reaching edge. I leave it alone at reaching edge as A. I don't update anything. And now I finally pull out node 4 and I found my path. Okay? So I got to node 1 2 times, but only the first time did I do anything, right? The second time I saw it was already visited, so I didn't do anything, right? I didn't look at it, I didn't update its reaching edge, etc. So now I invoke my backtrace routine, and my backtrace routine is just going to trace back, what was the reaching edge used at each node, and it's going to backtrace this way, right? The node that we used, the reaching edge we used to reach this node was A. That's this one. So that's the path it's going to find. But that path has a higher travel time. Okay, you can see that if I went this way, that's 10 seconds, but instead I went this way, and that was 15. So it found a path, but it's actually still not the shortest path. It was the first path that it found. It's the path that got to this node first, node 1 first, and kept going. But it turns out there was another path that went through more nodes, but actually is the better path, the shorter travel time to this node 1. And we never looked at that other one because we saw we'd already visited node 1, we didn't look at it again. Okay? So we wound up with a suboptimal path. Does that make sense? So it's better than depth first search, but it still doesn't guarantee we get the shortest path because we're still only looking at a node. Whenever we get to a node, we check if it's already been visited. If it's already been visited, we don't update anything. So if there's a better way to get to that node, we will not consider it. And that can lead to suboptimal paths. Let me very quickly show you this. There is a way to fix this. A way to fix this is we could store not a visited flag, but the actual shortest time that we use to reach each node. Okay, so now I'm storing a little bit different data. I'm not storing a visited flag. I'm going to store